All right, so let's resume the lecture with our new guest lecturer, my own cat with her own cone of shame. She's allergic to something in my house. I'm trying to figure out what that is. Uh, in any case, so let's continue on to the topic of how do we improve the performance, or on top of that, basically, what are the potential performance bottleneck? What affects performance, right? So obviously, this is similar to any network. When you build a topology, right, you have this thing called bisection bandwidth, which is basically defined as if I can cut the network in half, right? How much data can I pump through from one half to the other half? Just tell me how much data I can send through over time. It basically kind of infer, right? Not a direct, basically kind of not a super direct way to infer, but talk. It's also kind of cover things like network capacity and network throughput to some extent. There's also the routing policy that can affect performance. The routing policy dictates how likely can my policy create congestion. Imagine Google Map. How Google Map would route your car to the destination, because certain strategy would generate more congestion than others, right? How to deal with congestion. Basically, if there's a congestion, how to mitigate. Maybe we should go around, maybe we should reduce congestion. What should we do? How do you minimize the number of hops from the source to the destination? Basically, how do I get to the destination with the fewest steps? The number of buffer, the number of virtual channel, this can also impact the packet because they need to make forward progress, essentially, right? So, how do we increase the bisection bandwidth? This is probably, there's probably a simple answer, and there's also the more complicated answer. The simple answer is, I guess I can increase the link bandwidth. Downside is I can basically ended up consuming more area and power. What else can we do? Maybe different topology, right? Connect them differently. Rather than a ring, we use a mesh. Rather than a mesh, we can do a flattened butterfly. So new topology design can also impact this, right? New topology design. All right, and at some point, I feel like I need to take my cat outside of this room to make sure I can actually teach properly. You can also look into routing policy with the goal, basically, of I want high performance, I want lower congestion, and it should be deadlock and live lock free. All right, so we talked about deadlock already. Live lock is where things are moving, it's not freezing, but they make no progress, right? They make no progress. So people have been exploring the topic adaptive routing. Anyone ever use a Google map and then when there's a congestion, it suggests, hey, maybe you should go here. It will save you 5 minutes or it will save you 10 minutes. That is adaptive routing. Basically, the idea is first, I need to detect congestion. Then I would reroute the packet around the congestion. The benefit is, well, hopefully everything performs better, right? But here are some potential design problems. How do I make sure that my rerouting doesn't generate deadlock for someone else? Because I can block someone else from going in. Do I have live lock problem? I get reroute forever. For example, I can have a rerouting policy that looks like this. Like first go here, then I reroute here, then reroute here. Oh, there's no traffic here. And I keep going in this circle. Live lock, right? I never go out from this loop. Possibly you also can take more hops. You can go further distance, right? So eventually that might not be a smart decision at the end of the day, depends. And then you somehow need to have a complex support. Why? First of all, you need some way to detect congestion. How do we know that there's a traffic jam ahead of you, right? Imagine you're driving your car. What should you use to detect there's a traffic jam ahead of you? Because in the basic routing, you have no way to do that, right? So you need to convert the traffic information for everyone. So it does require some complex support for this. There's also the energy concern. Everything you do consume power. Everything you do when you send things through the link, they consume power. When you use the buffer, they consume power. When you need to go to the input-output ports, they consume power. Even things like when you're sitting there, you have leakage power. There's also this thing called leakage power, which is basically the power you leak out even though you do nothing, right? So these are dynamic power. Dynamic power are power that you consume when you're moving things. And then you have the leakage. It's the power that you also consume by not doing anything because you lose power. You lose energy. Electron move around, it does consume power. Electron leaks out because you're sitting there. Yeah, also consume power. The idea is, can we reduce this? All right. So what we said earlier is of routing topics, right? If you go to our reading list, there's many papers that look into this, right? On routing. We'll go into the detail in a bit. There's also concern over energy and power. So some people say, hey, buffer consume power. Can we eliminate buffer? Those some people is actually including me, right? I do have work on bufferless routing, minimal buffer routing. So the idea is, hey, can we use something like hot potato routing? Hot potato routing basically means that if I have a packet, I always forward them. I don't have buffer. I will find a link to throw them. I throw the packet all the time. The issue then basically is life locks, right? So you then need to figure out how do we solve this. You can pick the older slit, or you just do this like a younger slit, for example. One of the prime example of this is my own advisor's paper actually in ISCA 2009, basically do this hot potato routing, where he have shown that the performance is actually on par if the network is not super congested, right? So if you use equal bandwidth comparison for both mesh, which is this buffer mesh and bufferless mesh, right? Bless in this plot is a bufferless design. So in this plot here, Bless is the bufferless. We have no buffer here. We always do hot potato routing. And you compare flattened butterfly and mesh. If you look at this, right, you will see that if you have equal bandwidth comparison and your workload is not network heavy, there's no loss here. Why? On the X performance, here's the performance. You want to go high, right? And as you can see, Bless performance drop is not that big unless you have a really congested network. And this is run across 59 workloads. So it's mostly okay for low intensity workload, right? You can also look at, well, we keep a few buffer and deflect most of them, right? There's we do have a follow-up paper called MinBD, which is minimal buffer design. But most of the time we deflect. Most of the time we don't need buffer, except for a case where we have the side buffer that if I have to deflect, I can also put this in the side buffer. This is a paper we co-authored in NOX 2012. We actually was a best paper award candidate with our idea. Basically, there's also people who look into bufferless design, bufferless routing, low energy, low power routing. I will talk a little bit more about one of my work in a bit. But before we go there, let's then talk about the topology design, right? So what we know so far, we can have a bus which doesn't scale. I would even say it doesn't scale at all, right? The more component you added in, the less you can support, essentially. You can have a 2D mesh. You can have a ring, right? And we said, hey, one idea is you can have some design that increase the bisection bandwidth. One way to do this is to change the topology. One of the primary topology that people have been exploring, and it's actually get a lot of really positive feedback on this, is need to measure what my cat dropped. I'll do that in a bit. It's okay. is called flattened butterfly. So the flattened butterfly, comparing to the 4x4 mesh, right? The difference is this. You have the all-to-all connection in the X and Y direction. What I'm trying to say earlier, when you said all-to-all connection in the X and Y direction, what it means is, if I'm looking at the X-axis, I connect to everyone. If I'm looking at the Y-axis, I also connected to everyone. The key, really big contribution on this paper, on top of this topology design, is John Kim. He's actually currently a professor at KAIST. He proposed a way to flatten them so that it can be laid out on a 2D surface, basically making it possible when you have this crossing of wire, you can't literally cross them on the chip. Because there was short circuit, it's a 2D surface. You need to find out how to lay it out. Right? So the paper also talked about how to have a high radix network that is really cost efficient. And it's a flattened butterfly design. Right? That's one way you can change the topology. There's another follow-up work from a different group, Boris Grot. I think back in the day he was at UT Austin. He's in Europe now. So what he has is, hey, instead of a flattened butterfly, we can do something like this. On the X and Y, I use a bus. It's called MEX. Basically, design use a bus that connects the X and Y direction. It's more connected than mesh, right? Because you can go one hop from one location to another in the X and Y direction. The idea is called kilonox. I believe that it's also in a recommended reading. So if you want to check it out, feel free to, because I noticed a few of you are in the network area. This might interest you, right? So you can actually like use this design instead of the flattened butterfly. It's a good trade-off between a 2D mesh and a flattened butterfly. This would be faster than 2D mesh, less complex to design than a flattened butterfly. We also have another follow-up work on this high radix, highly scalable, that implement a design we call slim knock, which is like we take a dragonfly topology, then we explore the usage in a non-chip network. Right? If you're curious about that, I can also forward you the paper we publish. You can also look at hierarchical network design. And on the slide, I said just see my hierarchical design slide. So I'll switch to that in a bit. So let me put it up here. So actually give me some time to find the slides. My talks here. All right. So you see my new slide, just said design and evaluation of hierarchical ring with deflection routing. All right, awesome. So quick tidbit. There was another paper from HPCA 2022, if I remember correctly, 22 or 23, I think it's 22, by Huawei. They briefly cite my paper here, but if you look at the paper, you will see that the router design, the topology design is exactly almost the same as our design here. They use this for the AI chip, so it's really, really nice to see like the validation of the idea being used in the industry. I mean, in this case, Huawei kind of take our design, heavily inspired, I guess, by the design and put it in the paper. Usually when you write a paper like that, you would do a better job with the related work, to be honest. But yeah, to be fair, I mean, I can't control them. But yeah, so let me explain the idea quickly, right? So the idea is called the design and evaluation of hierarchical rings with deflection routing. And to quickly summarize, right? So ring doesn't scale well, right? So what you want to have is basically, can we have a hierarchy of rings? Basically put rings on a ring. Maybe on the third level ring, right? It can have some traditional design of hierarchical ring can be complex and not so energy friendly, because you need to have buffering and you have to have flow control. You need to figure out when to move from one ring to another. and all things in that front, right? So our solution is called hierarchical ring with deflection. Basically, we take the inspiration from the bufferless routing, put it on a ring, and find a way to guarantee lifelong freedom and delivery guarantee. Basically, our packet will eventually arrive at the destination and eliminate as much buffer as possible at no buffer in the local router, and most buffer are gone. And we found that it does provide high performance compared to the traditional buffer version of hierarchical ring, but it's way simpler, right? So let's quickly going over the background, right? If you look at network on chip, you have a scaling problem in the ring topology. For example, from 4 to 8 node, right? You will see that as the number of core grow, the performance will drop. I need to go further away to get to my destination. So an alternative of this is I can do hierarchical ring, a bunch of ring in the local network. Then I connect them in a higher level here, right? So people proposed this design actually a while ago, a long time ago, right? And the idea is basically I have the local ring level 0 and then the global ring level 1. I can even add another global ring, which is level 2. And the key benefit is I can reach far destination with fewer hops. I don't have to jump that many steps to get to my destination. All right. So let's evaluate some quick design, right? So if I look at performance on the y-axis here, you can see different bars show the scalability of the ring interconnects, but with different bisection bandwidth. Basically, each of these points I make the link wider. Basically, more things can be transferred through the link. And then I compare that with the performance of the hierarchical ring design with the 64-bit links. And as you can see here, that you see a really good scale in performance, right? So the hierarchical design, as your network size increase from 16 node to 64 node, you see better performance, and it beats performance of a ring, even with a high bandwidth link, right? But here's the complexity, right? You somehow need the buffering on both the global router and the local router. Then you have to control flow to kind of figure out where do I send packets over, how do I detect congestion, and etc. Basic control flow dictate how do I control the flow of traffic, right? So it means that my hardware need to make the decision on ejection forwarding. Now, if you look at the power, so earlier plot you saw performance, higher is better. Over here, in terms of power, lower is better. You want to go as low as possible. The high performance ring, it consumes so much power, but even with that, the hierarchical ring design also consume power. If you use a buffer version of hierarchical ring, it does consume power. Most of the time, it consumes more power than a 64-bit or 128-bit links for the ring. That comes from the design complexity. So what we want to do is to define a new way to design a hierarchical ring that would lower the complexity without sacrificing performance. And to do that, we use deflection routing. So our key idea is we want to get rid of buffer. Then we use deflection to simplify flow control. If I don't know, if I don't have the buffering to go next, I mean, I don't have buffer right now, I just forward them. If I cannot go to the desired destination, I deflect, going to a different path. So from the local router point of view, which is a small guy here, right? The way it works is I have basically I have a CPU or the cache or the memory controller from the core side. It can inject or eject into the router. I have the east and the west port. They can also take flips. Then I have arbitration that accept new flip. And the only job is to pass them along. This is simple because it's only one input, one output. I go from east, I go to west, I go to west, I go basically, if I'm from the east, I forward to the west. Even from the west, I forward to the east. Another decision, do I inject or eject? And that's it, right? It's really simple. So how do we make it even simpler? My goal, because there's only two paths, you inject, eject, or going east or west. So I can get rid of this buffer in the middle, right? I just have a direct forward part to where you want to go. Or if you want to get inject or eject, you go down. That's it, right? You now don't need buffer. You have incoming flit. You go to your destination. You're done. You don't really need a lot of buffer here. In fact, I don't need anything, right? So the flit can enter the ring. If the output is available, you go in, you go to the output. Otherwise, you don't enter the ring, okay? You don't need buffer here. And the crossbar is really, really simple. This is a really, really, really simple hardware. It's easy to design the router. It looks like this, okay? And we use deflection routing. Basically, if they want to go to the same path, in this case, let's say both want to go to the west. Both want to go to the west. I can deflect the injection. Instead of going to the west, I go to the east because, I mean, how bad can it be? I mean, obviously, you can take the other trip, right, around the router. So if you are injecting or ejecting, basically, you can get deflected and go this is a different direction. But if you're on your way, you don't get deflected. That way, you are allowed that eventually it will arrive at the other side of the ring and should be fine because it's a hierarchical design. You don't deflect that many hops. Then when you look at the bridge router, when you want to go to another ring, right? You have the global and the local ring, the one at the top level, the one at the bottom level. Now you just need to make the connection. The connections, this is a little bit more complicated because the local ring can come from the east and the west. The global ring also have the east and the west direction, right? So in that way, you have the 4 input, 4 output. Usually we have a crossbar in them to forward to the right place. You want to go somewhere, right? Now, I will go again. We want to make this as simple as possible. So the first thing we do, get rid of the buffer. Get rid of the complex crossbar. Now what we add is something simple. If you're on the west, you connect to the west or the east. So you can go from the east or the west. Let's say you are from let's say you're on the local ring. You want to go to the global ring. You have 2 choices from local, east global, local, west global. That's it. So instead of a more complicated all-to-all connection, I break this down so that I have 2 crossbar. Each crossbar only dictates 2 output because I can go only with east or west, right? I just need that. Then I add a really small buffering there because I mean, I don't want to deflect. I really want to buffer. So I buffer them there, but it's simpler. I don't need as many buffer. It's a much simpler crossbar, which turns out to give you a lot of benefit in terms of both energy and maintaining the performance, right? Now, here's my issue. I use deflection, which means I can have live locks. Live lock basically in the case where I get forward in the link forever. I never get to go anywhere else. So the next thing we do is how do we guarantee delivery, right? So there are multiple places we can have live lock or deadlock. Basically, the first place is called injection starvation. I have the source. I want to get into the ring. And I want to get into the ring. One situation I can run into is I have 2 packets going both ways. I have 2 packets going both ways. In this case, I cannot inject because they occupy my output port. I can stop here because every single cycle, there will be 2 packets using my desired output port, including my deflected output port. What do we do here? I mean, that packet stopped already. So if I detect a stop packet, our injection guarantee kicks in. The way it works is if I see a stop packet, after some cycle, I stopped injecting any new thing. So the throttle, I don't make any new flips being injected to the network. That guarantee that you can inject and go to the destination. Throttling provides an injection guarantee in the local level. Now, in the global level, you can have actually one more thing. You can have transfer starvation, which is basically the transfer between local to global. So let's say you have a fleet like this. You want to go to the global level, but that transfer FIFO, let's say that's your destination. Another flit sneak in. Oops, sorry. Another flit sneak in, use the buffer. So I get deflected. In the next cycle, the same thing happened. So in this case, I am stopped. I cannot go into the transfer cycle. So my transfer guarantee is if I get deflected, and I stop, something like this, what happened is after my 10th loop around, I will allocate the slot saying, hey, that slot is mine. Then I will just go in there. The future packet will be deflected, not mine. All right, so if I have this 10 loop around, I guarantee by reserving the slot, I inject myself in there. This provides a transfer guarantee. Now, the last thing is ejection guarantee. With ejection guarantee, we use the prior work proposed by my good friend, Chris Fallen. The work used this technique called retransmit once, used in the, I think used in the network. He basically applied to network on chip. The way it works is if I go to the destination, the buffer is full. Basically means I cannot take anything new. The problem is if that's full, I have to drop the packet, right? When I do that, the destination will allocate the buffer for me. The next time I retransmit, I guarantee a slot so I can go to the end. So this gives you the end-to-end delivery guarantee. So you have the local ring and a global ring. Injection guarantee, make sure you can go into the network. The transfer guarantee, make sure you can then transfer into the global ring. Then the injection guarantee, make sure you can go to your destination local ring. Then the transfer guarantee will make sure you can go to the local network. Now with the ejection guarantee, allow you to make sure you can get to the destination eventually. All right. So that's basically our solution called HIRD, hierarchical ring with deflection. We use deflection routing. There's no buffer in the local ring. We have a simplified bridge router and give you the end-to-end delivery guarantee. We do this by using simpler flow control, simple crossbar, simpler, faster local router, lower power in the bridge router, less area, simpler to design. For the results, we can basically simulate this whole thing. We basically use a 64 core and 16 core setup with the distributed L2 and a network that has the one flit local to global buffer and the 4 flit global to local buffer. Basically, it's a wider link in the global flit. In the local router is a ring, so I can use a 2 cycle per hop. On the global router is a ring with buffer, so it's more complicated. It needs 3 cycles. We run spec 2006. We got to be fair. That was like paper in 2014, so it was old. This at the time was a new benchmark. All right. So we run 60 workloads on spec 2006 application, comparing to a bunch of other design, including flat and butterfly. We have way more analysis on our extended version of the journal, basically a journal paper. We also compare to the buffer hierarchical design proposed in 1997 with identical topology, identical bisection bandwidth, and the 4 flit buffer on both local and global. So this actually have more buffering in the local router, right? System performance, we perform better than the ring design, including hierarchy, the buffer hierarchical ring across 2 different network sites that we try. So y-axis here shows performance, right? We get about 1.9% over the buffer version, right? Doesn't seem like a lot of gain, right? But be careful because this is performance. We want to design so that the performance stay the same, all right? So it actually provides better performance, which is good, all right? Because here is the key benefit, power. So if you look at the power plot, we actually reduce in a smaller network, the performance reduction is close to 50%. On a bigger network, it's actually better than most ring design, lower performance than hierarchical design by 15%. So we conclude that it actually consumes much less power. Router and flow control are much simpler. And we also evaluate the area and the critical path. Basically, this dictates how fast can your router be and how big will be your design, right? So we have this 16-node network with 8-bridge router. We verify this in Verilog using 45 nanometer technology. Okay, all right, 2003, that's the big technology node, but back then it was decently small. We saw that we have the area reduction of 50%, which is huge compared to the buffer version. The local router critical path, which means we can clock it faster. We actually get close to 30% compared to the buffer design. We also have many other results in the paper, including things like power breakdown, synthetic evaluation, energy efficient result, worst case analysis. We also have this is not a technical report anymore, it's a full extended version of the paper in the journal. The multi-threaded evaluation, the average 90 percentile latency, max latency comparison to many other topology, and sensitive analysis with different link bandwidths, different number of buffer, right? And to be fair, we do get a lot of feedback from the reviewer. We try to submit this to like many top conferences that got rejected. Most of those are like, hey, what about comparing to this, comparing to that? So we put them up in an extended version because we have more room in the journal version. All right. So to conclude, ring doesn't scale well. So we have a new design that are using hierarchical ring with deflection. So it's simpler. It guarantees live log freedom. It guarantees delivery. It eliminates all buffer at local routers and most buffer at the bridge. It provides higher performance and energy efficiency than traditional hierarchical ring, and it's simpler. So that's the idea of hierarchical ring with deflection. So that kind of concludes the talk part about my work, right? So let's go back to here. The next thing we haven't touched yet much into that, except for the hierarchical ring work, is flow control. Okay, so what is flow control? So when you have a wormhole routing, it's a form of flow control because it's control how the packet flow throughout the network, right? But then you can kind of figure out, okay, with this, I can then adjust the traffic. You think about it, like I can adjust how the traffic and the car would flow around this network of packets, network of links, right? So one strategy that is really common is called the credit-based flow control. If I use a router and I pass through a bunch of router, I would pass back the number of available buffer. Basically, right now, let's say my buffer has 10 routers, 10 buffer left. I have 10 slots. When I have new packet coming in, I pass them information back. Say, hey, I only have 10 slots. All right. This gives the source information about how much room I have left. Okay. So this allows me to make sure that whenever I go forward, I need enough room. Knowing how much room I have in the future guarantee forward progress and a good flow control. If the buffer is really full, I know it's really full, I can do something with it. The bad side of this is I need to make sure I have enough buffering. So the credit-based flow control only forward packets, only if you have enough credit. If you don't have enough credit, you wait. All right. You can do on-off flow control. On-off flow control is a little bit different, where if it's on, I can accept new flip. If it's off, I don't accept. Okay, it's as simple as that. If it's on, there's no traffic here, you can come in. If it's off, so much traffic here, don't come in. Okay. And the congestion basically reduces performance here because you have a shared link, shared resource, shared buffer, right? So network congestion basically reduces system performance. Can have packets that are crowded, in this case, say in the middle router. If you want to go through that middle router, you better expect delay because everyone wants to use it, right? In some cases, you cannot even go into the router. It can't, there's no room, right? That's congestion. You can also look at adaptive routing. XY routing is deterministic. You always figure out the path. You always go there. Adaptive routing means that if I detect congestion, I use a different route. You can do it in a using local decision. The next hop determines where I go. The hard problem is how do you guarantee forward progress, because you can keep going in the different path until you never arrive at the destination. right? Let's say there's a major traffic jam in Bangkok. Sometimes Google Map will reroute you and you keep going rerouting. It might be longer, right? If you make local decision-based thing, you might not making forward progress. You can also try to use a global decision strategy where you determine the path in a global fashion. The problem here is you have tons and tons of packets in a network. So how do you coordinate in a large network, right? So there are many works, again, in the recommended reading in our reading list that are touching these topics, right? There's also this thing called the turn model. The turn model basically dictates what turn can you make? Can you make the left turn? Can you make the right turn? This is there to ensure deadlock-free network in the adaptive routing. So you can do west first. You route packet through the west exit first, then south and east and north. This guarantees that packet will be going to the east side. This makes sure that forward progress is made. You can do not last. Basically, route packet through the north exit last. It guarantees the packet will be route to the north exit eventually, right? These guarantee that packet will make forward progress. Basically, there are many papers. Actually, there's many fundamental paper on the trend model, how to ensure there's no deadlock. Okay. There's also deflection routing. You saw it already. I deflect. I don't keep deflect. Right. It can be used to reduce congestion as well because it's kind of adapting to the path. If there's so many things going there, I deflect. Okay. There's also the paper called Regional Congestion Awareness. This is more like how do I detect congestion? How do I detect traffic jam going forward? The idea is I want to propagate congestion backward. So packet flow is to the right, where I send a packet from left to right, from left to right. I have different ways to do RCA, Regional Congestion Awareness. I can do the status information flow from right to left, from right to left. Is one, you can do one direction. You can do fan in. Fan in means that I also take both top and bottom information, send it backwards. I can also do the quadrant, top half, bottom half, right? The idea is I allow information to be used, forwarded back. Paper proposed by Paul Gratz. Again, he's also another professor right now. It is proposed at HPCA 2008. It's called Regional Congestion Awareness for Load Balance in Network Ownership. You can also do something like source throttling. The idea is I stop packet from going into the network if the network is super congested, right? Basically, imagine a traffic that's super congested in Bangkok, 5 p.m. Right? Bangkok, 5 o'clock in the evening. You look out your window, you see cars everywhere. If you drive out now, you're getting home at 8 p.m. You spend 3 hours in traffic. Oh, I still don't believe how that's possible, but yes, that's my life, right? So one of the better strategy is I wait. I don't go into traffic right now. I wait until the road is more empty. Then I go out. I arrive at instead of 8 p.m., maybe 8:30, right? But I spend less time on the road. So this is an idea called source throttling. We actually apply the idea on the network. The paper we published was called Heterogeneous Adaptive Throttling for On-Chip Network. My good friend is the first author. I'm second author on this. The idea is basically I have processing elements, right? P are the packets. And when I have the network that is super congested, the middle cloud that you see here is like a network. There's so many packets in there, so many cars. What I can do is instead of putting more packet in, I throttle. I don't let them inject into the traffic. So when I throttle, the network will slowly drain the packet. And when the network is draining and there's not a lot of packets, then I reduce the throttle so that I can go to the destination, right? So with this design, this is an abstract view of how we do it, right? There are many key questions. Basically, how do we throttle? What's the rate, right? And what application should throttle? how much to throttle. So the naive mechanics is one thing I can do. I can throttle everyone at the same rate. But here's the problem, right? Some application inject more into the network. Some application inject fewer packets into the network. So if I run, say, 8 copies of 2 different applications, GrowMax and MCF. MCF is really intensive. GrowMax doesn't really inject much into the network. As you can see here, if I throttle GrowMax, I'm not really emptying anything in the network because MCF would keep injecting new flips into the network, right? So actually, if you do this, if you make the wrong decision, actually worse performance, what you want to do is to throttle MCF so you see fewer packets in the network. So in this case, both profit, both improve performance because the network is more free. There's not a lot of traffic. Both can make forward progress in a better fashion. So our idea is to make it application aware. You throttle the right application, and we want to make sure it's aware of the network load, throttle with the right rate. To be application aware, sorry about animation back here, but basically should be 1 and 2. We measure the network intensity using L1 miss per 1,000 instruction. How often are you injecting things to the network? Then you select what application to throttle. Because if you leave too many applications unthrottled, you flood out the network. But then if you measure things by MPKI, right, you can measure how much can the network handle. You sum up the MPKI of the application. If it's lower than the threshold, you leave them unthrottled. Anything more than that, they're being throttled, right? So the network intensive are being throttled. Network non-intensive, you can use the network, but you're not using much of the network anyway. Then there's a rate in which how much you want to throttle, right? Because the network load matters. You want to throttle not too much or not too little. So we would measure the current network load with the target load, because for each topology, you know how much it can handle in terms of traffic. And we would dynamically adjust the throttling rate based on this. So if it's more than the target, we throttle more so that it goes down, reaching the target. If it's less than the target, we throttle less. So it's actually more network, more packets in the network. And with this, right, we make sure it can be adjusted to change in the application by doing it epoch based. So every 10,000, 100,000 cycle, right, I would measure the application MPI, measure the network node, and then at the beginning in the next epoch, I would adjust the rate. So that's kind of the key idea on how we do source throttling, right? So as you can see, there are many, many things you can do. I'm not saying one is better than another. It's different. They're trying to each making the network on chip better. I go into more detail about source throttling and hierarchical ring because those were my paper, and I have the talk for that. I have the slide for it, to be honest, so I can make the slides, right? But at the end of the day, there are many, many things you can do. That concludes the topic about network on chip. And as I promised you, I'll kind of continue on with about like it'll be more smaller discussion on how to give a talk, how to make a slides, how does a research talk looks like, and what should be your goal and things like that. So we'll do that after the break. Let me pause here. If you have any question, feel free to put it on the chat. I will go look at the chat right now and see if there's any question I should answer. All right, so that's a wrap actually for the topic. All right, thank you so much. Don't forget, next week we have the exam. I will release the sample exam right after this, and the week after, as I told you, it's a holiday, so we'll, instead of doing a presentation, you will do the recording. I'll do the Q&A on that. All right, thank you so much, folks.